sorry, I'm moving things around on the screen. You can't see that, but okay. So this is section 1A. All right. And this is called sets and set operations. All right. Now, the first thing to define is what is a set. So a set in mathematics is a collection of objects. And that is pretty general. That is not very specific of what on earth a set is. So to kind of help, I'm going to show you an example of a set. So let's say that A is the set 0, 1, 2. Okay, it just has 3 different numbers in there, and this is an example of a set. The objects would be the 0, 1, and 2. All right, it's not super interesting. It's kind of a boring set, but that is an example of a set. Often we use capital letters to represent sets. So capital A, I'm defining to be that set. Okay. The next thing I should define is what an element is. Okay. The element or the elements are the objects in the set. Okay. So the elements in set A are 0, 1, and 2. Okay, there's 3 objects in set A. All right. So those are the elements of set A, and we have a notation for this. The symbol, which is kind of like an E. Okay. It means is an element of, and the symbol, which is that E crossed out, means is not an element of. Okay, let's look at an example of what on earth is that talking about. So that is saying, for instance, 0 is an element of A. Okay, that's how this symbol is used. It's saying that 0 is an element of A, meaning that 0 is an object inside A. Okay, I can also say 1 is an element of A, 2 is an element of A, but I could not say that 3 is an element of A because 3 is not inside this. So I would need to cancel that. I would need to write the not an element of, okay, because it's not inside. So that is an example, and the definitions, as vague as they are, the definition of a set and the definition of elements. I often think of sets as like a list. So of a grocery list, is, or even an ingredients list, is just a list of items. Okay, but it doesn't necessarily mean order wouldn't really matter for a grocery list. I guess if you were trying to get it in the order of the grocery store, but a grocery list doesn't need to be in a particular order. So that is to say that this would be the same thing as the set 2, 1, 0, because order doesn't really matter for a list. These are just a list of objects, so you can put them in either order. Generally, we write them in order. This is in numerical order since they're numbers. When they're letters, we'll write them in alphabetical order, but it doesn't have to. Okay. The other thing with sets is that we would never write something with duplicates. Okay, so you would never write 0, 1, 1, 2. Okay, you wouldn't write that. You wouldn't write duplicates of a number. Okay, things only need to be listed one time. All right, so we don't write duplicates for sets because it's just a list. We don't need we don't require to have detailed where it would be listed more than once. So we only write it one time. Okay, so that's what sets are. What is an special? There's some special sets, and one of those is called the empty set. The empty set is so special, it has its own symbol, and that's just a circle that's crossed out. This is the empty set. And the empty set is a set that does not contain any elements. Okay. The empty set does not contain a single element. It is completely empty. Okay. There's no elements. If I tried to write that out, the empty set would equal something like this. Okay. It would just be completely empty. And the point that I want to make is that before we had the set A, which was 0, 1, 2, okay, the set A contained the number 0. The empty set does not contain the number 0. It has 0 amount of elements, but 0 is not inside the empty set. So this would not be a true statement when where I would say the empty set equals the set of 0. That is not true, okay? Because 0 is an object and the empty set is not contained. So this is not true, okay? So I'm going to put equal, does not equal, okay? So the empty set does not contain the number 0. It doesn't contain anything. It's complete emptiness, all right? So hopefully that makes sense, but the empty set is very special. We're going to deal with it all the time, but it's the set that has no elements inside of it, okay? It has no elements of its own, all right? And the next thing I should define is the subset. A subset of another set is equal or less than, but all elements must be contained. Okay, so what is going on there? Well, we had the set A equals 0, 1, 2. Okay, so that was our example of a set. Now, I want to show you an example of a subset. Let's say that we have set, I don't know, D. Let's say that the set D is just 1 and 2, okay? This would mean that D is a subset of A, okay? So this means that D is a subset of A. Well, how do I know that? Because all of the elements contained in D are also contained in A, okay? We have a notation for this. we have a notation for subset. This is denoted with this symbol, which is kind of like a tipped over U. If you can imagine that, like I had a U and then I tipped it over. It's denoted this way, okay? So if I showed that in this example, D is a subset of A, okay? All of the elements in D are contained in A, okay? When I think about subsets, I kind of think about inequalities that we may have seen in algebra, where you have less than or equal to, less than or equal to, greater than or equal to, that kind of thing. Well, it's kind of like saying D is less than A, but even more so, it means that all of the elements in D are contained in A. Okay. Now, this may seem kind of strange, but A is also a subset of itself because all of the elements in A are contained in A. Okay. So A is a subset of itself. Okay. That can be kind of confusing that would be true, but the definition of subset is that all the elements have to be contained within the other set. So A is a subset of itself. D is a subset of itself, but D is also a subset of A. So I should write that out in words. Is a subset of A. Okay. And we could also say that D is a subset of itself. But what we could not say, we can't say this, that A is a subset of D. I can't say that because all of the elements in A are not contained in D. What am I talking about? There's the element 0 here, and it is not contained in D. So that means A is not a subset of D. It can't be. Okay, even though it's the number 0, it's still not in D, so it cannot be contained. So I'm going to write not a subset. I'm going to cross that symbol out. Okay. So A is not a subset of D. All right, because all the elements are not contained. All right. Okay. One important thing to note, we went over empty set first, and then we went over subset. And one thing I want to make perfectly clear is that the empty set is a subset of all sets. Okay, the empty set is a subset of all sets. How can that be? Because there's nothing inside of the empty set. So that means that is listed within all other sets. So the empty set is a subset of itself. It's a subset of any set A, any set D, any set at all. The empty set is a subset of all sets. Okay. So that can be kind of confusing, but it is true. All right. So I wanted to make sure I mentioned that. I believe it comes up in the homework. One thing I have been doing, but I didn't mention, is I've been using this notation, and these are called braces. So when I talk about sets, I've been using these braces in the notation to kind of list the items. So I haven't been using parentheses or just writing them out, but I've been using these braces. And these braces are a way to use notation to signify that we're talking about a set. Okay, so you'll see that in the homework. You'll be asked to use that notation, but you're just going to use braces. If you're looking at a keyboard on the computer, the braces are there. They are shift and then the bracket key. So they are listed. They're kind of close to the enter button or the return button on your keyboard. Okay, but you'll see that on the homework as well. You will see that notation, and we use that notation a lot. So one thing that's kind of tricky with this kind of thing is when we talk about elements and we talk about subsets, kind of a hard problem, or kind of a trick with this notation is that technically 1 is not a subset of A. Okay, that's getting kind of particular about the notation, but it is true. 1 is not a subset of A, but the set that contains just the number 1 is a subset of A. That's very particular. We're going to see that on the homework. There's some trick questions there, but that is technically this statement over here, 1 is a subset of A, is technically not true because just the element of 1 is not a set. Okay. Same line of thinking, the number 1 is an element of A. That's true. It is inside A. But the number 1, well, how could I don't think I could combine these ideas. I was thinking maybe I could do the other one, but I don't know what that would be. Yeah, so I'm going to erase that idea. I don't think I can say that. Yeah, okay. So that should be enough to kind of see with this notation. I'm going to show the homework. We'll see some examples with that. The next thing we need to talk about is some operations with the with these sets. So just like with arithmetic, we'll have adding and subtracting and that kind of thing with sets, but it's all very specific, so we'll have to go over that now. Okay. And those that have taken this class before, I'm sure will recognize these words. And the first thing I want to talk about is what's called the union. Okay, this is the union of sets. Okay, we use it so often, it gets its own symbol, and it's denoted just capital U. Okay, I put parentheses around that, but it's just denoted the capital U. This is one of those things that it's usually easier for me to just show an example rather than try to define it. It will seem more complicated than it is if I try to define it. But if I have the set A is equal to 0, 1, 2, and I have the set B is equal to 3, 4, 5, then the union is going to be kind of like adding the two sets. Okay, so the union of A union B will be something like adding these together. Now remember, when we're talking about sets, we're never listing anything twice or anything like that, but we're going to put these together. So for the union of these, I'm going to put them together. I'm going to add them together. And so the union of A and B will be 1, 2, 3, 4, 5. So the union put all of the elements in A and all of the elements in B all together. So now they are all of the elements. Okay, so that is what the union is. The union is a set that contains all elements in each set. Okay, so that is what the union is where you're kind of like adding. That's kind of roughly because it didn't actually add any numbers to it, but it's a bit like adding sets. Okay. Oh, this is a good question. Nick asks, can the union contain more than one set? I'm assuming yes, or more than two sets. Excuse me. So I think Nick is asking, um, can you do the union of more than just two sets? Could you do the union of, say, three or four or five? Yes, you can. I'm assuming that's what Nick was asking. So
Yeah,
let's
yeah,
add
that's
another.
essentially what it was. Yeah.
Oh, very good. Yeah, so absolutely we can. If we have the set C equals the number, um, let's do 2. Let's write it like this, sorry. So braces 2, 3, and 6. Okay. So what would be the union of A, union B, union C? Okay. So one thing, I'm using this as an opportunity to go over, we see that there is some duplicates here. We have 2 and 3. 2 is listed in A, 3 is in B, and the only new material we have is the number 6 here. So the union is all of the elements listed must be contained. So this would be 0, 1, 2, 3, 4, 5, 6. Okay, so the union will contain all of the elements, but only once. We have no duplicates there, so it'll only be listed one time. Okay, so great. Yeah, you can do it with more than one. You can do it with more than two, of course. Generally, we stop at 3. 3 is kind of where we stop. It doesn't have to. I mean, you could keep going, but we usually stop the idea in this class um, at 3. Okay. Um, Now, the other one that is really just like the other side of the coin is the intersection. Okay. So the intersection of sets denoted, which is like an upside down U, okay? And we don't have a symbol like that on our keyboard, so that's kind of a nuisance, and we'll see how we get around that. But the intersection of two sets are, I should say, is a set that contains the elements in common. Okay. So for our example here, we have plenty to work with. If I do A intersect B, this are the elements that they have in common. What elements do they have in common? A is 0, 1, 2. B is 3, 4, 5. These elements don't have anything in common. So that is the empty set. They have no elements in common. However, A intersect C do have elements in common. They have the number 2 in common. So that would be just the set 2 that contains 2. And B intersect C would be just the set that contains the number 3, okay, because they only have the number 3 in common. So that's how you can do intersection. Yeah, so intersection is just what do they have in common, and the union is you're putting them all together, you're adding them together. So I think of this as in common. Okay. And union is like adding them up. Okay. Okay. So that would be, that's very, very important that we understand that. But from there, we can move on to some more topics. And one thing that is a little bit confusing is that this is called the universal set. Okay, and the part that's confusing about the universal set is that it's denoted also just capital U. I try to put these little tails up top. I try to remember to do that, but it's just denoted the capital U. The universal set is a set that contains all objects. Okay. So in our example, we had A equaled 0, 1, 2. We had B equaled 3, 4, 5. And we had C equaled, I think, 2 and 3 and 6. And so the universal set for this is the set that contains all objects. So this would be 0, 1, 2, 3, 4, 5, 6. Okay. So the universal set is the set that contains all of the objects. And you could also say that the universal set is the union of all sets. Okay. It is the union of all sets. The union of all sets. Now, of course, this is all of the sets that are of interest to us in that particular problem, but it's the union of all sets, and so we see that in an example. If you take the union of all the sets listed, that is what the universal set is. Most of the time in homework problems, you will see that the universal set is listed. They will give you the universal set, but not always. But that is what the universal set is. It's the set that contains all of the items, and it is also the set of the union of all the other sets. Okay, so that is the universal set. The thing that's confusing is that it is also denoted a capital U, but I hope it's clear that when we use union, that is in conjunction with two sets. It's an operator. It's operating on these two sets. And that the universal set is its own thing. It's not, it's kind of its own thing. So here you can see that it's not in between two other sets. Okay, so that's the universal set. That's often confused. I hope it's clear and clear enough to begin the homework. Okay, so that is the universal set. The next thing I would like to talk about is called the complement. The complement of a set. Okay. Now, the complement of a set is the negation of a set And this negation it's like thinking of the opposite. It's kind of like thinking the opposite of the a set. So I always think of it as the opposite. Okay. What do I mean by the opposite? Well, let's look at one of our examples here. We have plenty to work with here. So this is denoted, I should say, denoted A parenthesis, one parenthesis there. That signifies that it is a complement. In some books, they actually do a little C up here, but all of the homework is not written that way. It has just this little note here, and that is signifying that it's a complement. And this can be read as not A, okay? So it's not A. I think of it as the opposite of A, right? Well, what would be the opposite of A here? It's all of the elements that are contained in the universe that are not in A. So for this example, A complement would equal all of the elements in the universe that are not in A. So that would be 2, 3, 4, 5, 6. Okay. So that would be the complement of A, right? So it's just simply the opposite of A. You could also write the complement of B, which would be all of the elements in the universe that are not in B. So that would be 0, 1, 2, 3, 4, 5, 6. Okay, so that would be B complement. And C complement would, well, we have 2, 3, 6 for C. So that would be 0, 1, 2, 3, 4, 5, 6. That would be C complement. Okay.
Just a quick question. Would 2 be considered part of like the complement?
Oh, are you talking about for A?
Yeah.
Yeah, that looks like that was a mistake. I apologize. So that should not have been there because 2 is an A. So that should have been 3, 4, 5, 6. Yeah. Thank you. Joe, was that your question too? Okay. Yeah. Sorry about that. I was getting a little distracted. So that is not part of it. So A complement would be all of the elements not listed. So that'd be 3, 4, 5, 6. There we go. Okay. Okay. One thing I should say, and this may sound a little weird, but the universal set could also be written as A unioned with A complement. And this is true for all sets. This is actually true for all sets. If you think of you and then everybody in the world that is not you, that's everybody, right? So if you think of the universal set as every living person, well, if you are the set A complement would be everybody else other than you. And if you put those together, that's everybody. So for all sets, the union of A and A complement is the universal set. It would have to be. And you can do that for any set, okay? Even the empty set, believe it or not, you can even do that for the empty set. You can say that the empty set unioned with the complement of the empty set, that's everything. It has to be, because there's nothing contained in the empty set. If you take the complement of the empty set, that must be the universal set. So that works for all sets, okay? So I thought I might mention that. Sometimes that shows up in the trickier problems, okay? All right. So that's complements. We're gonna deal with complements a lot. It might not feel very complimentary, but that is how we define them in finite class. And one of the last things in this section that we need to go over, which is really important, it's just we can now get to it. And this is called De Morgan's law, okay? And De Morgan's law can be written in a few different ways, but it incorporates the idea of the union, the intersection, and the complement, okay? So, for instance, A union B complement. So what I'm doing there is I'm putting A union B in the parentheses, and then I'm going to union those, and I'm going to take the complement of those, okay? Now, De Morgan says that we can rewrite this as A complement intersect B complement. That's one version of De Morgan's law. What does this mean? This means that the opposite, or the negation, the complement of the union of A and B is equal to A complement intersect B complement. So it's what do those have in common is the opposite of the union. Okay, so that's one version of De Morgan's law. The other one that you can write is A intersect B. Complement could be written as A complement union B complement. Okay, that could also be written that way. So what does that mean? It means the opposite of the intersection is A complement union B complement. So this is De Morgan's law, and we're going to play with this a lot. But this is the earliest time we can introduce that. So this is De Morgan's law. Now, the way I think about it, practically speaking, is I think about it as we're kind of distributing this complement, kind of like exponents in algebra class. When you took algebra class, you would have exponents that you would have to distribute through the power law. And that's kind of what the complement is doing, is it's being distributed. So what is the opposite of A but A complement? What is the opposite of the union? The intersection. What is the opposite of B? B complement. Okay. Similarly, opposite of A is A complement. Opposite of the intersection is the union, and the opposite of B is B complement. Okay. So this is how you can write De Morgan's law, and that is what it means essentially. And we will play a lot with that in time. Let's see. Speaking of time, what time is it? We're about 5 after. That's good. That's good. So I think there's one other thing I want to mention before I show the homework, and that is called the Cartesian product. Okay. The Cartesian product is how you would multiply sets. We've kind of talked about how you would add sets, and we've kind of talked about how you could just find what's in common with them. We haven't really talked about how to subtract sets yet, but this is how you would kind of multiply sets. So in a way, this is, product is referring to multiplication, and this is denoted as an X there. Oftentimes with these things, it's a little bit easier to see an example than to describe it in words. So that's what I'm going to do. So if I have the set A is equal to 1, 2, 3, and B is the set, let's say the letter A and the letter B. That should be good enough. I'm going to show what the Cartesian product is, okay? So A cross B, and this is a lot of writing, I'll tell you at the beginning. First, it's with 1 and then A, and you have to write in parentheses. So that's 1 in A, that's 1 in B, and 2 in A, 2 in B, then 3 in A, and 3 in B. Okay, so that is what A cross B looks like. And that is a set of the ordered pairs. It might kind of look like points to you. When you took algebra class, you dealt with points a lot. You talk about X and Y, you would talk about graphs and that kind of thing, and the point 1, 2, or the point -3, -4, that kind of thing. Well, that's kind of what this is. And so if we do these sets, if we times them, we can see this is what the Cartesian product will look like. Order does not necessarily matter, but I tried to put it in some type of order so it's easier to look at. But this is what the product of the two sets would look like. That's what it means. If you're going to go into like computer science and programming and that kind of thing, well, programming languages also have that, but sometimes they're listed as different things. So this is what a product would look like. I will call to your attention for a moment that there are 3 elements in A and 2 elements in B, And when I did A cross B, how many elements were there? 1, 2, 3, 4, 5, 6. 3 times 2 is 6. So that's a way of, you can at least predict how many elements should be in the cross. Yeah, Nick says, essentially you're just distributing the numbers with the variables in essence. Exactly, that's it. So yeah, it's, it is fairly simple. I hope it's coming across simple. But the Cartesian product is, we're just putting the elements together in these ordered pairs. Okay, that is what a Cartesian product is. That is what we mean by multiplying within the world of sets. Okay, getting close to 10 after. That's probably enough lecture to actually show some homework problems. I'm just looking over my notes and making sure I shouldn't show any more. There's a couple tricky things that maybe I should write down. This is just kind of some of the hard stuff. Let's get some votes here. Is this true or false? Would you say that any set A unioned with the empty set would equal A? Would you say that that's true or false? A union with the empty set is just A. Is that true or false?
True.
True. Does everyone agree that that's true? Do we have any people that say false? So union is we're adding them together. So all of the elements in A and all of the elements in the empty set are being added together. Well, there's no elements in the empty set. So when we put these together, we just get the original set. So exactly, I think Nick said it. So exactly as Nick said, that is true. Okay, very good, very good. What about the intersection? A intersect the empty set, is that equal to A? True or false?
Is
That's
it
what we-
false because it doesn't have common elements?
Exactly right. It must be false because what do they have in common? All the elements in A, all the elements in the empty set. Well, what they have in common is the empty set. What they have in common is the empty set. So I'll write the true statement here. The true statement is that A intersect the empty set would equal the empty set. That is true. This is the true statement. Okay. Awesome. 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 Good job, everyone. I had another trick one here. Let's talk about universal sets. So we talked about A. Let's say that we did the universal set intersect with any set A. Would that be the set A itself? True or false? Now remember, the universal set is the set that contains all elements. So would it be true or false? The intersection between the universal set and any set A would equal A. Is that true or false?
Is that true?
That is true. That is true. It is true because A is contained in the universal set because all of the elements are in the have to be inside the universal set. And so what they have in common is A. That must be true. Let me think. Okay, one last tricky one, and then we'll do the homework. Is let me get the right pen here. The universal set complement, is that equal? Is that the same thing as the empty set? Are those equivalent? True or false? Is the complement of the universal set the empty set? Oh, I see something in the chat. Joe says that's true. I think it's true. I think it's true. The thing outside, if you take all of the elements and you throw them away, you're left with no elements. That would be the same thing as the empty set. So I believe that that is also true. Okay, great. Awesome. I'm going to save these notes. Okay, so I can post them later, and that's what I'll do. I'll post them in that discussion section. And now what I'm going to do is I'm going to stop sharing my screen for a moment, and I'm going to pull up the homework, and we will be able to look at, I will at least describe the homework and kind of show what it looks like. I might even do a few problems to get you going. And that should definitely jumpstart the process of the homework. So that was section 1A. We should have enough information to begin the homework for section 1A. So let's do it. We have 14 problems, and I'm going to flip through it, kind of describe what's going on. You will have similar problems, but not the exact same. You'll see that mine is already completed, but you're going to have very similar numbers, very similar problems, but not the exact same. So let's talk about this. We have the set A, 1, 3, 5. We have the set B, 2, 3. And we have the universal set as 1, 2, 3, 4, 5. So what do they have in common? Well, you can see that I already have the number 3 listed. Is that true? Well, yeah. So you can see that the element that they have in common there is just 3. So I selected just 3. Okay, I could have selected more, but I don't want to. That's all they have in common. The union of the two sets, just as before, is kind of like adding them together. So you have 1, 2, 3, and then 5. There's no 4. And just because they both have 3 in them, we don't put that twice. So we just want to put all of the elements that are contained. Okay. And the last one's a bit tricky, so let's talk about that. So we have A intersect B complement. So, well, what is B complement? B complement for this problem is all of the elements that are outside of B. So that would be 1 and 5. Oh, and it looks like a 4 is also in the universal set. So we have 1, 2, 3, 4, and 5. So that is B complement. All right. Well, what is A intersect B complement? It's what they have in common. That's what these have in common. A is 1, 3, and 5. So we're looking, what elements do these have in common? I would say they have the number 1 in common and the number 5 in common. So I would think to select 1 and 5. Okay, so that's why I did that. Okay, so hopefully that makes sense. It asks about B complement, so I had to find B complement. It wasn't given, so I had to find it, but it wasn't too bad since they gave me the universal set. Okay. All right, well, hopefully that makes sense. All right, for this problem, we have to type our answers instead of doing a multiple choice. We're given 3 sets here, A, B, and C, and we have to find the intersection. So you can see that I found the intersection, the elements that are in common of A and B. The union of A and B are all of the elements in A and B. You can notice that nothing is listed twice there. It's only listed once. And then we get into slightly trickier problems like B union C intersect A. That's a little bit trickier than something we've done before. Or B union C intersect A. That's a little bit harder. So maybe we should talk about that. I highly, highly suggest the way to do these problems is to do parentheses first, just like we were doing algebra. So in algebra class, what would you do? You always did the parentheses first in PEMDAS. Well, I would suggest doing that for finite too. So I would advise you to figure out what the union for this, the parenthesis first, and then find the intersection of that set. So what would B union C be for this problem? Well, B union C would be all of the elements in B and C. Okay, so what would that be? That would be 0, 1, 2, 3, 5, 6, 7, 8. Okay. Then I need to find what does that have in common with A. Well, A is 2, 4, 6, 7, 8. So I just need to find what they have in common. First, is there a 2 here? Yeah. Is there a 4? No. 6? Yes. 7? Yes. 8? Yes. So I think it would be, let's see, B union C, both have 1. Yeah, so this would be 2, 6, 7, 8. Okay, so it's what do they have in common with the union. So first, I had to find what that union was. I solved the parentheses first, and then I found what they had in common with A. Okay, so hopefully my process makes a little sense. Here, we have B union with C intersect A. I would also suggest to do the parentheses first rather than trying to solve the whole problem first. So if you have C intersect A, that is, what do those two sets have in common? So let's see what they would have in common. So 2, no. 4, no. 6, no. 7, yes, they have 7 in common. They have 8 in common. So I can say that C intersect A must be 7 and 8. Now I add in any elements in B to this set. So I have 1, 2, 6, 7, and then I also have 7 and 8. So I believe it would be 1, 2, 6, 7, and 8 in that total set. Okay, that's my process. That's how I would solve the problem. That's how I did solve the problem. Okay, so I hope that makes sense. I hope that will help you. Okay. Here we have some subset true and false questions. We kind of worked on this before, but let's see what we can do. Is the empty set a subset of this set? Well, the empty set's a subset of all sets, so that must be true. It must be true. Is the element X a subset of this set? Well, that is not true, as we went through in lecture. That is not true because X is an element. It's not a subset. I would need some braces around that X for it to be true. And is the empty set an element inside this set? And that would also be not true. That would be false because the empty set is a set and not an element, and it's not contained in there. So that would also be false. So hopefully that makes sense what that's referring to now. All right, this one puts it in words for us, and it's saying the union and the intersection. So hopefully that would make sense to you now. It says it will vary, but J is the set of odd digits. K is the set of digits that are greater than 5. So hopefully with this information and that written out, that will be easy enough for you to find out. Okay, so those are actually written out in words. You don't have to deal with the symbols. So hopefully that will be easy enough for you to find problem 4. this is very similar. Problem 5 is very similar to problem 4 in that we're given the set of digits 0 through 9. J is the set of even digits. Even numbers are divisible by 2 evenly. And set K contains digits greater than 4. So that would be 5 through 9. And you would find the union of those sets, the intersection of those sets, and the complement of K. Okay, but yours may vary since these are randomized. Okay. For 6, you're asked for the Cartesian product. We talked about the Cartesian product briefly in a lecture. And I will say for this, you have to type it all out. And that is the biggest nuisance for this problem. But you can see I had to type all of that out. That's how you do the problem. So that's usually the questions I get for this type of question is it's not accepting my answer. And it would be a good idea to be sure that you are typing it correctly. So once you've typed it, you can click submit answer, and it will tell you what you have entered, what it understood to be, and then if it's green, that would be correct. Okay, that's how it signifies a correct answer. I probably shouldn't show too much of this since this is multiple choice, but here it's asking what would be which one of these Cartesian products would the order pair 4, 1 be in? Well, I have 4 in A, and I don't have a 1 in B, so I know it wouldn't be A cross B because I couldn't get the 1 here. So the only way I could get it is A cross A. That would work. And then B cross A would also work because you could have the 4 and then the 1. Okay. So you'll have questions like this, or with the order pair 1, 2, how could you possibly get that? Well, if you had A cross B, you could get 1 and 2, of course. So that would be one way. Or 4, 4. Since there's a 4 in both of them, you could do A cross A cross B to get 4 and then 4, and then B cross B also. All right. So that's the type of questions you'll be asked for that problem. Here, this is very similar to something we did in class. You'll see De Morgan's law listed there. Maybe I will show that. So A complement, that is A. The complement is the elements that are outside of A, so you'll want to list those. And then for something like A union B complement, I would suggest first finding what does A union B equal, and then find A union B complement. So yet again, I would suggest do the inside of the parentheses first before you try to solve the whole problem. So I would, excuse me. Sorry about that, everyone. Okay, are you guys still there? Can you still hear me?
Yeah.
Okay, yeah. I have a family member that's in the hospital. That's probably what that was about. But so A union B in parentheses complement. So you want to work on the inside the parentheses first. So that is how I would suggest to do such a thing. So I highly suggest starting the problem out with working inside. And also for this one, so we have A complement intersect B complement. I might find A complement first, then B complement, and then find A complement, B complement. You can see what's outside both. Okay. If you're patient enough, you probably could do it just by inspection and just looking and going out of these two sets, what's outside of it. But that's how I would do it. As I would do it piece by piece. I would see what is A complement, what is B complement, and then what is outside both of them. So that's how I would tackle that problem. Okay, these are some true and false questions. I should probably leave you to it, and they do vary between student and student, but you get limited attempts for the true and false, so take your time. Take your time with those, okay? Go slowly. You might even save them for last, okay? For something like 10, we have set A, B, and C. If you have A cross B, it's just asking how many elements, okay? It's not asking what is it, just how many elements. For A, here we have 2. For B, we have 2. So that'd be 2 times 2. There is 4 elements inside A cross B. B cross C, again, 2 elements, 2 elements. 2 times 2 is 4. There's 4 elements in A cross C, or B cross C. How many elements are in A cross B cross C? Well, that would be 2 times 2 times 2. That must be 8, okay? 2 times 2 is 4, times 2 is 8. So there are 8 elements inside A cross B cross C. And then the final one is to actually write out what that must be, okay? And you can see what my answer would look like here. So the first one would be 4 P and then R, and then I would do 4 P and then V, and then 4 Q R, and so on, okay? But knowing how many elements are inside is a really good way of keeping track. That way you can see, okay, I know how many there should be. There should be 8, and then now you can kind of know what to expect. You can know what to expect, so you know if you're missing any. This is another true and false. I should probably leave it to you to decide. And yeah, I probably should leave that one. And I probably should leave this one for you. I should probably leave this one to you. I'll at least read it to you. This is problem 13 and 1A. Let the universal set be the set of college students. V be vegetarian college students. S be college students who smoke. And F be the set of freshman college students. Which one would represent the following? All college students are not vegetarians and who do not smoke. Okay. So this not here, not, let me get my pen tool. Not, that's talking about complement. So V complement, S complement, okay? When it says and, that is for both sets, okay? So that's what do they have in common. When it says and, that's talking about what do both of them have in common. So that would have to be the intersection. If it said or, that would be the union. Okay, if it said or, then it would be either one. That would have been the union because we add everything together. But since it says and, it has to be in both of them, and so that must be the intersection. Okay, so we can see how that one works. I think there's only one more problem. Okay, let the universal set U be the set of all U.S. House representatives. R, that's the Republicans. S is the set of representatives from South Carolina, and F is the first term representatives. All representatives who are not Republican or are not in their first term. So for this, we're talking about not. So not Republican would be R complement. Not in their first term would be F complement. And since it's or, this is talking about the union because it can be in either one. It's not restrictive. It doesn't have to be in both of them. It can be in either of them. So that would be the union. Okay, since it's talking about or, it's talking about union. It can be in either one. If it says and, it has to be in both of them. Okay. Okay, well, that's what the first homework looks like. So hopefully it's not too intimidating at this point. Are there any questions?
No, I don't think so.
Good. So hopefully it makes sense of how to get to the homework, how you can tackle the homework. That homework will be due before class on Wednesday. Now I would like to take a 15-minute break. We'll come back. We'll talk about section 1B. And we'll do the exact same thing except with section B. So I'll go over some lecture and then we'll go over the homework and I'll answer any questions there might be and then we'll call the night. So that is my plan. So let's take 15 minutes from now. We'll come back and we'll talk about section 1B. So I'm going to realize I was not recording that. Let's see. So I'll open up our course. Okay. So we go to assignments. And I want to look at homework 1B here. Open section 1B. 15 questions. Let's see what we can find. Okay. First question is asking which of the following corresponds to B intersects C. I will say this. WebWork is terrible about displaying images. Okay. When you first open this, a lot of these are going to be empty. Of course, mine are all displaying because I've already looked at it. My computer's already saved the images. A lot of times you're going to have to click these images over and over, refresh the page to eventually get them to show. It's a known problem, but that is the truth. So you will have to continuously refresh the page until all of them show up. Don't hesitate. You just keep clicking them. If they show up, then you can refresh the page and show it. So it's going to be annoying for sure, but they will eventually show up. Okay, so B intersects C. This is what B and C have in common. Actually, the first one here works. We have A, B, and C. What do B and C have in common? They have this little sliver here. We can see that this is not true. This is the part of B that has nothing to do with A, the part of C that has nothing to do with A. That's not what B and C are. This would be B union C. So that could be easily confused, but this would not be B intersects C. And then this would be B intersects C minus A, but that's not what we want. We want all of this. So that can't be true. Okay, so that's why I would choose the first one. Yours will be randomized of what it's asking, but that's how I would choose my answer. Okay, B intersects C complement is kind of like asking what is B minus C. So we want the part of B that has nothing to do with C. That's what we're going to look for in this problem. That would not be this. That's everything but B and C. B and C complement. We don't want that. What we're looking for is B minus C. This would also not be right because we have outside. We just want the part of B that has nothing to do with C. So we're really just looking for this part here. And that looks like it's this one. So this would be the part of B that has nothing to do with C. So just be these two pieces right here. So that's how I picked that one. Okay, now this one's a little bit more complicated. It has a parenthesis here. And how I would suggest to do it is I would suggest thinking about it with the parentheses first, understand what the parentheses is talking about, and then you can tackle the whole problem. So the parenthesis says A union B. A union B is putting all of A, all of B together. And then we want to intersect that with C complement. So what does that have in common with not C? It's kind of like saying A union B minus C. That's what this statement is saying. A union B minus C. That's what it's saying. So we want just all of A, all of B, take away the C parts. We don't want C. Okay, so that would not be true for this part. No, we want A and B. We just want to take away C. And this is not it. This is kind of looking like it here. We have A and B, and anything to do with C is taken away. So this is what we want. We don't want the outside here because we're asked about the intersection, or at least in my version of the problem, we were asked about the intersection. So we don't want this outside. That would be a different problem if it was a union. Okay, so we don't want that. So this would be the correct answer for A union B intersect C complement, which is like A union B minus C minus C. Yeah. All right, this is very similar, except it just talks about regions, and it's a multiple choice question. Select all the regions that would be shaded with A complement union B complement. Well, with this, we can recall De Morgan's law. That would be the same thing as A. The opposite of A complement is A. The opposite of the union is the intersection. The opposite of B complement would be B. So by De Morgan's law, we have the opposite of the intersection. We have A intersect B complement. So it's everything but region 1. We just don't want region 1. So that's what De Morgan would say. And so that's how I would simplify that problem for myself. Okay. So hopefully that helps. All right. Select the regions which must be shaded. We did this. This is in the lecture notes. A complement intersect B. That's like saying B minus A. Okay. So it's the part of B that has nothing to do with A, and that's just going to be region 3 here. Okay. All right. This one has 2 parentheses, so I would certainly understand what each parenthesis is talking about before I tried to tackle the whole problem. So A complement intersect B complement is A union B complement. That's what this first part is. And then this part is kind of like talking about A minus B. Okay. So A union B complement, A union B is region 4. Oops, I should do a different color. So A union B complement is region 4. And A minus B is over here to region 2. And we want to put those together. Okay. So the union of these 2 ideas must be region 2 and region 4. So that's how I would work through that type of problem. Okay. 7 should be fairly easy to do. If the others made sense, you're just trying to solve what this one is. You have many different choices there. So that should be fairly easy to do. Same as this one, you only have one Venn diagram to understand, and you just need to choose the one which best represents that. Very similar to this. You are looking for which would best represent this Venn diagram. This is B minus A, so you just want to maybe look at your notes and see which one would work best for that. Very similar to this, you only have one Venn diagram, and you just want to see which would work best to represent what this is. This is obviously A complement. Okay, this one we should talk about. Enter true or false depending on whether the statement is true or false. You must enter T or F. True or false will not work. Okay, the number of elements inside the set 2 is 2. Well, that is not true. I put false, but why did I put false? Because the number of elements in the set 2 is actually 1. There's only 1 element in there. Okay, that's what the number notation is asking. How many elements are inside the set, the number of elements inside the set that just contains 2 is just 1. There's only 1 element inside that set. Okay. This says the number of elements inside the set that contains 3 is equal to 1. That's true by the same logic I used up here. So that's why that would be true. Okay. The number of elements that these have in common, the intersection x, y, z intersects v, w, z is 1. Is that true or false? I say that's true. They have z in common, and so this would simplify to the number of elements of just z, and that's just 1 element. So I would say that that's true. I would say that's true. Okay. Any questions about that one? Does that make sense how I did that?
Yeah.
Good, good, good. Okay. Okay, so for this one's going to be kind of confusing, but A and B are subsets of the universal set. A intersect B, A intersect B complement, A complement intersect B, and A complement intersect B complement are non-empty. Select which of the following to form partitions. Now remember what a partition is. A partition means there's no overlap, and there's nothing outside those sets. Okay. So you can see what I wrote as the answer, but maybe I should explain how I got it. So B and B complement. There's nothing in common there, and there's nothing outside them. So technically, that would form a partition. You could write a partition as B and B complement. That's fine. There's nothing outside B and B complement, and there's nothing in common. So you can write it that way. Okay. By the same logic, you could also write A and A complement. There's nothing outside A and A complement, and there's nothing in common. So you can write it that way. All right. What about something like A intersect B, A minus B, B minus A, and the outside? Well, I claim that if you go piece by piece, there's nothing in common with these statements. Say 1, 2, 3, 4. There's nothing in common between those. And if you put those all together, they would form a partition. Okay, so technically that's true. So why does A and B, just A and B, not work? Well, because they told me that A intersect B is non-empty. So there would be an overlap. And there's things outside A and B. There's also an outside. So there is an outside, so that wouldn't work. Okay, so A and B complement, that also is not enough. It's not enough. Okay. So hopefully that's a good enough hint to get started. Hopefully the logic makes sense of what I'm talking about to understand a problem like that. Okay. For this one, I'm going to work it out, I think, fully. Sets X, Y, Z form a partition in of the universal set U. The number of elements in Z equals 7 times the number of elements in Y. The number of elements in X equals 2 times the number of elements in Y, and Y equals 7. Okay. So there's a lot going on here. But the first thing we have to understand that these are partitions. If we don't understand that these are partitions, there's no way we can solve the problem. Okay? We have to understand what that means. So what does a partition mean? It means they have no intersection and there's nothing outside them. So I can draw a little picture here and I can say I have X, Y, Z. So I can write X, Y, and Z here. Okay? And there's nothing outside them. And there's no intersection. Okay? They told me that Y equals 7. Okay. They said y equals 7, so I'll just write a 7 there. All right. They said that x equals 2 times y. X equals 2 times y. Well, y is 7, so I would say that that equals 14. All right. And z equals 7 times y. Z equals 7 times y, so 7 times 7 is 49. So what does the universal set equal? The sum of those. And I have 70 there. So hopefully that makes some sense to you of how I could break down a problem like that. Even though these are given to me in relation to one another, I can still solve the problem by understanding what a partition is, and I can break it down into pieces, and then I can solve the final problem. Looks like there's a question here. Nick said, well, if I can say what he said, Nick said that made so much sense when drawn out. Yeah, it really does. If you break it down into little pieces, and that is a goal of mine to show. If you break things down into tiny pieces, all of this stuff is not very hard. If we can really break it down, most of this stuff is pretty easy. That's how I hope it comes across. It's actually pretty easy. If you know what to do, and you understand what the problems are asking, for the most part, this stuff's pretty easy. I hope. Okay, set A, B, form a partition of the universal set. The universe is 99, A equals 4 times B, and C equals 7 times A. Find the number of elements in the following sets. What does A equal? What does B equal? What does C equal? Well, this one's a little bit different than the last one. In the last one, they told me I was solving for the universe, and they told me what one of the sets equaled. Now they tell me the universe, and I have to find what do they equal? What do each one equal? So I'm going to draw it out. That seemed to work last time. So maybe we'll have more luck. Now, I know that the universe equals 99. I know that that's true. So that's what they said is true, so it must be true. Okay. They told me that A equals 4 times B and C equals 7 times A. Okay. Well, how can I work with that? Well, A equals 4 times B and C equals 7 times A. Okay. But they just told me that A equals 4 times B. They just told me that. So I could rewrite this as C is 7 times 4 B's. Okay, if A is 4B, this would be 7 times 4B. Since I know that A is equal to 4B, that's what they told me, I could sub in, just like our algebra class, I could sub that in, and I would have 7 times 4B. So what's that? That would be 20AB. So I have 4 B's here. I have 28 B's here. I have 1 B here. The universe equals the number of elements in A plus the number of elements in B plus the number of elements in C. So if I add these up, I could solve for B pretty easily. I could say that 99 equals 4B plus B plus 28B. And now it's just like an algebra problem. It's just like an algebra problem. So we have like 4x plus x plus 28x, just like our algebra days. Okay. From there, you can solve for b. You want to solve for b. Now what you'll do is you'll add these up. Okay. I'm going to get rid of the x part. So we got 4, 1, that's 5, plus 28, 33. What color do I use? Pink. Drawing tool. So I have 33 B's equals 99. I can divide both sides by 33, and I get B equals 3. So there we go. Now I know what that equals. So that means A must equal 4 times 3, 12. And that also means that C has to equal 28 times 3. What's that? 28 times 3, 84. If we break it down into pieces, it's not so bad. But trying to tackle everything at once is too hard. So hopefully that gives you a bit of a hint of how to do that. I'm going to save a picture of that one for you. Hopefully that's will get you started on that homework problem. And our friend Timmy has some marbles here. We're going to talk about them. So Timmy has some red marbles, some blue marbles, some yellow marbles, and he has a total of 294 marbles. He has 6 times as many red as blue, 7 times as many yellow as red. Determine how many marbles of each does he have. Now, I would claim that this is very similar to the past 2 problems we've done. Because it's a partition problem. There's no marbles which are both red and blue. They're either red, blue, or yellow. Okay? So this is a partition problem. All right. So we let's get my drawing tool here. So we have red, blue, and yellow. We have a total 294. Okay. We have 6 times as many red as blue. We have 7 times as many yellow as red. Determine how many of each color we have. So from there, if you use the tactics we just did in the previous problem, you should be able to solve how many marbles are there. You can see what my answers are already. Yours will be somewhat randomized. We should be able to take that information we did in the previous problem and apply it to this last problem and see this is a partition problem. Just because it's a story problem doesn't mean it's any different. And you can take those tools and apply it to this problem as well. So I'm going to leave you to this one yourself. You can see the answers. I'll leave you to do it yourself in your homework. So I hope that's enough of a running start to tackle this homework. Okay, you've seen all the homework within class, so I'm hoping that when you're on your own and you're doing this homework, it will be very approachable to do. Okay. All right. So that is that's class. That was the first class. Yeah. So are there any questions? Any questions?
I don't think there's any questions.
Okay. Okay. So I'll leave you to it. That is it. Those 2 sections are due next time. And I'll answer homework questions for roughly the first 20 minutes. But that'll only be for partial credit. For full credit, you'll need to do all those yourself. I'll post this video. Usually it takes a little bit to render. But hopefully I'll post it tonight in that discussion section. The lecture notes are already posted, so you can find them there. And you should be able to get started on your homework. So let me know if you run into any trouble. But you should know what is expected at this point. So I'll end the meeting, but I hope you have a good evening. I hope you have a good tomorrow, and I will see you Wednesday. Okay? All right. I'll stick around if there's any questions, but